Vectors is one of those topics that A-level students often find harder than it needs to be. And from my experience, the issue isn't really the maths itself. It's that you can often get hit with notation before understanding what a vector really is. So that's where I'm going to start. In the next 15 minutes, I'm going to walk you through every single thing the spec asks you to know about vectors. Sections 10.1 right through to 10.5. And it's going to seem basic, but what I'm really trying to show here are the foundations that's going to make the topic click. And so by the end, you'll have the core principles locked down, so that when it comes to approaching exam style vectors questions, you've got the good amount of raw material you need to execute those properly. Here's the thing that most A-level teachers won't tell you about vectors. The mechanical maths inside this topic, the arithmetic, is genuinely simple. We're talking about addition, subtraction, multiplying by a number. There's no calculus, at least not at this level. There's no algebraic manipulation that much harder than what you did at GCSE. Because vectors is one of those rare topics where the concept matters more than the calculation itself. But every textbook basically starts off by drowning you in notation. Bold letters, arrows on top, columns, I's and J's flying around, but they never actually tell you what a vector really represents. So before we touch any of that, what actually is a vector? Well, there's many definitions, but a good way to think about it is that a vector is a set of instructions. That's it. Go 3 steps to the right, 2 steps up. That's a vector. Walk 5 meters north, then 3 meters east. That's another vector. It's a recipe for moving from one place to another, and the numbers tell you how far. The direction tells you which way. That's the whole concept here. And once you get that in your head, you'll have the raw material to basically apply that knowledge in a more exam style context. So make sure to watch the full thing in order to get a full understanding. Now I know what a lot of you guys are thinking. Wow, this guy's got a face. And that's true, but also what you're probably thinking is, where did he get that information from? And that is from 10.1 on the spec. 10.1 says you need to be able to use vectors in 2 and 3 dimensions. You need to know column vectors. You need to know I and J unit vectors in 2D and I, J and K vectors in 3D. So here's how all that connects in plain English. A vector in 2 dimensions is just 2 numbers stacked on top of each other. The top number is how far you move in the X direction, and the bottom number is how far you move in the Y direction. That's a column vector. 3 over 2 means go 3 across, 2 up. In 3 dimensions, it's basically the same thing, except now you've got a third number underneath for how far you move in the Z direction. Across, up, forward. 3 numbers, 3 directions. Now the IJK thing trips students up for the reason that it could easily be misunderstood to be algebra, but it isn't. It's just a different way of writing the same instructions. I simply means 1 step in the X direction. J simply means 1 step in the Y direction. And K simply means 1 step in the Z direction. So when you see something like 3i plus 2j plus 5k, all that's saying is 3 across, 2 up, 5 forward. Same vector as the column, different notation, but ultimately it's the same thing. Okay, now for 10.2 we're going to be going through some key naming concepts, but don't think that this is it and just click off the video, because you definitely want to go through this part, because once you get to the end where we start talking about exam style questions and using what we know to solve those problems, you're going to wish you had this bit. Make sure to internalize this concept so that once you get to the end of the video you'll be a lot more sorted for it. Now the spec wants you to calculate the magnitude and direction of a vector and then convert between component form and magnitude direction form. Magnitude is simply just the length of the vector. If your vector is the instruction go 3 right, 4 up, the magnitude is how far you've actually travelled in a straight line from start to finish. And to find that, you don't need a new formula. You already know that formula, and that's Pythagoras. 3 squared plus 4 squared. 9 plus 16, 25. If we square root that, is 5, so the magnitude is 5. Okay, and the notation is just 2 vertical bars around the vector, which represents that we're talking about the length of the vector, the magnitude. In 3D, it's the same idea, but you've just got 3 numbers to square instead of 2. X squared plus y squared plus z squared, and we square root the lot of it. And direction is the angle the vector makes, usually with the positive x-axis, and that's just basic trigonometry. Okay, so tan of theta is equal to opposite over adjacent. And going the other way, from magnitude and direction back to components, we just use trigonometry in reverse. So if we've got a vector with length r at an angle of theta to the x-axis, the x component is r cos theta, and the y component is r sin theta. That's the same right angled triangle, we're just solving for a different side, and the spec wants you to be comfortable in both directions, so don't just practice one way. Now, unit vectors. The spec specifically calls these out. A unit vector is a vector with a magnitude of exactly 1. So you've got a vector going 3 right, 4 up with a magnitude of 5. And you want the unit vector in the same direction. So you just divide everything by 5. Now it's 3/5 right, 4/5 up. Magnitude is now 1. So same direction, but just shrunk down. The reason I'm spelling this out is because every time a unit vector question comes up in an Edexcel paper, that's the method. Find the magnitude, divide each component by it, and it works the same way every time. Now 10.3 is where a lot of the geometry lives, and as a result, it's very easy to get tangled in this specific section. The spec says, add vectors diagrammatically. Perform the algebraic operations of addition and multiplication by scalars. Understand the geometrical interpretation. Triangle and parallelogram laws, parallel vectors. So that's a big list, but here's the underlying truth. Remember, if a vector is a set of instructions, then adding 2 vectors is just following one set of instructions after another. Walk 3 east, 2 north. Then walk 1 east, 4 north. Where do you end up? 4 east, 6 north. That's vector addition. You add the x's, add the y's. In 3D, you add the z's too. It really is that basic. That's also the triangle law. You draw the first vector. From the end of it, you draw a second vector. The arrow from where you started to where you ended up, that's your answer. The triangle law isn't a rule that you need to memorize, but it is a picture of what addition actually does. The parallelogram law is the same thing rotated. If we draw both vectors starting from the same point instead of one after the other, and then complete the parallelogram, the diagonal from the start point is your sum. It's the same answer, but different picture. Multiplying by a scalar, which is just another number, is even easier. Now it says 12 east, 8 north. Same direction, just 4 times longer, so you've scaled it. And here's where parallel vectors come in. 2 vectors are parallel if one is a scalar multiple of the other. That's the technical way of saying same instructions but different scale. It's like having a recipe for a cake and then a recipe for a double cake. Okay, a cake that's 2 times bigger. Same flavor but just a different size. So when an exam question asks, show that these 2 vectors are parallel, what you're actually showing is that one is a number times the other. So find the multiplier and then sort it. I'll take a second to take all that in because 10.4 is where it all comes together. Now, position vectors is something that the spec explicitly calls out, and it's something that a lot of exam questions will lean on. And here's the difference between a normal vector and a position vector. And it's one distinction that seems simple, but it's very important. A vector is an instruction, how to get somewhere. But a position vector is a location, where you are. The trick is, in the vector world, we describe a location by basically saying, if you start at the origin, follow these instructions. That's the whole concept. So the position vector of a point A is just the instructions to get A starting from the origin. So if point A has a position vector A, that means that from the origin, follow vector A and you land at A. And from the origin, follow vector B, you land at B. Now, and this is the formula at the heart of every position vector calculation you'll do. The vector from A to B is OB minus OA. To go from A to B now, you've got two options. You could go directly, or you could go from A back to the origin, and then from the origin back out to B. Vector wise, those two paths are going to give you the exact same answer. From A back to the origin is just minus A. You're undoing the instructions. From the origin out to B is plus B, so the total journey is minus A plus B, which we just write as B minus A. Now the reason I'm hammering this is because that one formula is literally at the heart of every position vector calculation you'll do. To find the vector from any point to another point, you simply subtract the start from the end. And that's always end minus the start. Now distance between 2 points is just the magnitude of that vector, and that's Pythagoras again. Okay, so in 2D you square the differences, add them, and then do a square root. In 3D it's the same thing, but with the z term. Once you just understand it's Pythagoras in disguise, you don't need to memorize it or anything. Now, okay, great, we've got the vector theory covered, we've got the principles. Now, how are we going to use these vectors to solve problems that the exam wants us to solve? Now, 10.5 says you need to use vectors to solve problems in pure maths and in context, including forces. Now, I'm going to be going through exam style questions more properly in a different video, but one example that's worth calling out, because the spec mentions it explicitly, is finding the position of the fourth corner of a shape, like a parallelogram. Here's the trick, and it is a trick, not a method. A parallelogram has two pairs of parallel sides. Now in a vector world, parallel and equal length doesn't just mean similar, it means the same vector. Identical instructions. So in a parallelogram ABCD, the vector from A to B is exactly the same as the vector from D to C. Not parallel to, not proportional to, but identical. Which means if you're given A, B, and C as position vectors and asked for D, you set up the equation. Vector AB equals vector DC. Substitute in your B minus A's, rearrange, solve for D, and then we're sorted. They give you A, B, and D, but then ask for C, it's the same idea, just different sides. Always look for two sides of the shape that should be equal as vectors, and then set them equal. From there you can solve. The reason this question shows up so much is because it tests three things at once. Your understanding of position vectors, your understanding of equal vectors, and your ability to manipulate B minus A formula. If you followed everything in this video, you've already got all three, but you just need to recognize the pattern. Now all the contextual stuff such as force, velocity, acceleration, etc. that's all covered in mechanics, and you shouldn't get confused with this because all that really is in mechanics we're just applying what we know about vectors now. And nothing really changes in the underlying concept, right? A vector is a vector. It doesn't matter what label you put on it or what type of vector you use, all vectors are going to behave the same if it has vector properties, and it is indeed a vector. Now look, if you follow this video all the way through, chances are you've got everything you need from a conceptualization and intuitive understanding perspective for vectors, so you can start attacking exam style questions properly. But knowing it from video is one thing, but drilling it for exam prep is another thing entirely. And that's why I've developed a platform that's basically helping students practice these questions and really hone in on the exam style questions rather than just theory, so that they can aim for an A star. But make sure to click the link below to sign up for the second cohort, where you'd be eligible for 50% off.